Okay, this is a video on explaining, like looking through example 6 out of the exponentials chapter, which is topic 6 in your textbook. We're looking at the second lesson, and this is example 6. And this problem is about using exponential regression to create models. So what you're going to be doing in this problem is looking at a bunch of data points and then using your calculator to create an exponential model. So I'm going to play the video that's on the textbook website and then pause it at certain times and jump over to a graphing calculator on the screen and show you what they're doing behind the scenes, because they don't show you everything that they're doing on the calculator and how to do it on the calculator in the video. So let's go ahead and start the problem.
Randy is making soup. When the soup is done cooking, it is piping hot. Randy wants to serve the soup hot, but not too hot. How long should Randy let the soup cool before serving it if he doesn't want to serve it cold? To solve this problem, you need to know a few things. First, how cold is too cold? If Randy lets the soup sit for too long, it will eventually reach room temperature, about 68 degrees Fahrenheit. Next, how hot should the soup be when it's served? Randy would like the soup to be about 10 to 15 degrees above room temperature, or around 80 degrees Fahrenheit. Lastly, you need to figure out how quickly the soup is cooling. Randy measured the temperature at various points over the first 20 minutes and recorded the data in a table.
Okay, so right now, what we want to do is jump over to our calculator, and we're going to type these data points into the calculator. So here's my TI calculator, and I know the layout obviously is a little bit different because I have my viewing screen over here on the right and my keys on the left, but it's basically, they're all the same keys as you have on a regular TI calculator. The first thing that you want to do is go to the Stat menu right here in the center. And we're going to go into Edit, so you can hit 1 or you can hit Enter, and we're going to type all our data in. So you can see right now I have some random data in. I don't want that there. If you have any data in your calculator, what you need to do to clear it is to go up until the list title is highlighted, hit Clear, and then the down arrow, and you want to do that for all the lists that you have data in currently. And one last one, clear and down. Okay, so list 1 is always going to be your X data, which for us is the time. So we're first starting at 0 minutes, and then 2 minutes. 3 minutes and 30 seconds is 3.5 minutes, so 3.5. Then 5 minutes, and then 7.5 minutes, and then 10 minutes, and then 15 minutes, and 20 minutes. And list 2 is the temperatures that they're giving us. So we're starting off with 212 degrees, which is the boiling point. Then 185, then 170, 162, 145, 138, 125, and finally 117. Alright, come back to the video and let's pick up where we left off.
You can use the graph of the data to help in choosing an appropriate model. The graph shows the temperature decreasing as time increases. Let's try the simplest model first, a linear model. Here's the best fit linear model for the data. You can check how well the model fits by looking at the residuals. There is an upward curve to the residuals, so a linear model is clearly not the best fit.
I'm pausing the video right now. Regression is not something we've talked a lot about, and residuals is something we've never talked about. But basically, what they did when they moved this data from here down to here and created something called a residual plot. Basically, the residual plot is just if you pretended this diagonal slanted line was actually a flat horizontal line, which is what they're doing by moving it down here to the x-axis. The residuals are just how far above or below the line each point is. So you can see this first green dot it's a good amount above the line. That's why it's a good amount above the x-axis. And this point right here, the second one, is only a little bit above the line, so it's only a little bit above the x-axis. And these next 4 points are all below the line, so that's why they're below the x-axis. This point is on the line, so it's on the x-axis, and it's above, so it's the one that's above. Residual plots are good because what you want to see from a residual plot is just a totally random scatter of points above and below the x-axis when you create a residual plot. And if you have a random pattern of some that are above and some that are below, but in general that they're all really close to the x-axis, then you've got a good model. But if you have a clearly curved pattern like we have here, then your model is not a good model. If all your points are above or all your points are below, you don't have a good model. What you want is to see a random scatter of points that are pretty close to the x-axis. And we're not really going to focus on how you create a residual plot in this lesson. Just take it on faith that because the residual plot shows a curve, that means this model is not linear. And it's obviously not going to be linear because we're studying exponential functions anyway.
We could use a quadratic model, but a quadratic model has its own problems when put in context of the cooling soup. You can see that the revised model predicts the soup's temperature will increase rather than continuing to decrease. This does not make sense when talking about Randy's problem. Since the soup is cooling to room temperature, it should always be decreasing, but it also shouldn't go below 68 degrees Fahrenheit. So the model should also be decreasing, and it should have a horizontal asymptote, or lower limit at 68. One type of model that is decreasing and has a horizontal asymptote is an exponential decay model. So you can use an exponential function to model the change in the soup's temperature over time.
Okay, so you can see here that they have this horizontal asymptote of 68 degrees, and that's going to come into play for us in this next part.
A graphing calculator can help you create an exponential model for data using exponential regression. First, you need to put the data into a table on your calculator. Some calculators will only calculate exponential regressions for data values that approach 0.
And approaching 0 is what our calculator is going to do right now if you just leave the points this way. So they're going to tell you next what you do to approach some value other than 0. Like in this problem, we're approaching 68 degrees instead of 0 degrees.
Even if your calculator does not require it, subtracting 68 degrees from the temperatures puts the information in the context of Randy's original problem.
So what we're going to do is we're going to subtract 68 degrees from all of these temperatures in list 2. And because there's 8 points here, that you might be like, oh my god, I have to do 8 different things. But there's actually a nice quick way to do this. And here's what you do. You're going to go to list 3, and you're going to go up to the title of list 3. And what you're going to do is take all of these values and just subtract 68 from them, just in one step. And this is how you do it. So all these numbers are in list 2. So the way you can do this is we're going to do list 2 minus 68 degrees. So that needs to be the title of list 3. So what you're going to do once you're on list 3 is you're going to hit second 2, and that gives us the command list 2, and then subtract 68, and just hit enter, and then it automatically subtracts 68 from all of them at once.
Since how hot the soup feels depends on how many degrees above room temperature it is. Use the exponential regression feature to calculate an exponential model based on your data.
So they just say, use this exponential regression model, and they don't tell you where it comes from or how to get to it. So let's look at how we get an exponential model. The first thing that's important is we want to make sure that we are using the data in list 1 and list 3 when we do this calculation, and that we don't touch list 2. So what you're going to do next is you're going to go back to your main screen. You're going to hit second mode, which quits out of your whatever menu you're in. And then you want to find the exponential regression model, and that is in the stat button. And then you want to go over to the calc menu. And basically you're just going to scroll down until you see exponential regression. Obviously it's not on this first screen, But, oh look, it's right here. It's choice 0. So you can, once you're highlighted on it, you can either hit enter or you can hit 0. It really doesn't matter. I'm going to hit 0 just to show you that it works. The newer calculators are going to give you a menu like this. Obviously, X list is list 1, and our Y list is not list 2, it's list 3. So to change that, you want to hit second and then 3, and that changes it to list 3. And frequency list, you can ignore that. You want to store your regression equation in Y1 so that you can come back and use it again later on. The way you put Y1 here is you hit vars, which is variables, then you go to Y variables, function, and then Y1. And then you're going to come down here and hit calculate. And you'll notice right here, I don't know if you saw real quick, but it said exponential regression, and then it said list 1, comma list 3, comma Y1. If you have an older TI model, like a TI 83 Plus, that's the way you're going to have to type it in. You're going to go to stat calc 0, and instead of this menu popping up, your screen is just going to say exponential regression, and then you would type list 1, so you'd hit second 1, comma, second 3, comma, vars, y vars, function, y1. And once you have that command line along the screen, then you'd hit enter, and you would get this same calculation that we just did. This thing right here, that's what your screen would need to say. So once your screen says that, then you can hit enter, and it will tell you what the equation is. So our exponential model is 126.35 times 0.949 to the x power. And obviously you can see this is a decay model because the b value is less than 1.
Since Randy only measured one temperature at each time, there is no need for a frequency list for the data. Your calculator should give you the values for a and d in the exponential function, as well as some information about how well the model fits the data. When you substitute those values into the general form of an exponential function, f of x equals a times b to the x. You can use the graph of the function to find where f of x is between 10 and 15 degrees above room temperature. Tracing the graph of x.
So let's go over and look at our calculator and see what this looks like. So in order to go, like if I go to a graph right now, you might see something, you might not. You can see that our function comes a little bit through here, but you might have a different window where you don't see anything show up right now. But what you want to do is get to a window where you can see all your data points from the table and you can see your function. So there's one nice trick way how to do that. What you want to do is go to second y equals. You want to turn the plots on, and you want to make sure you have this scatter plot thing picked. And we want to go down and do x1. We're doing list 1 and list 3, so change your y list to list 3. And then you want to go to graph. Actually, no, what we're going to do is we're going to hit zoom and then number 9, which is zoom stat. Zoom stat will always take you directly to your coordinate points that were plotted. And you can see we have all our points and we have our function that comes through here. But notice if I hit trace, see if right now I'm on the plots, if I hit the down arrow, I'll go to the function. You can see my y value is 75 degrees. But I want to get down to where I'm only like 10 or 15 degrees above room temperature. And clearly I'm about to run out of space, and I'm at 46. So I want to increase my amount of space. So I'm going to go to my window, and I'm just going to increase. Right now this is like 22 minutes after he takes the soup off the stove. I'm going to go out to like 60 minutes. And then I'm going to go down, like right now my lowest y temperature is 32 degrees, but I want to be down to see 10 to 15. So I'm going to go all the way down to where it would be 0, and then go back and look at my graph. So you can see this exponential model comes down. If I hit trace, I'm back on the points. I want to go down, so I'm on the function. And I'm just going to cursor over until I get down to like 15. And you can see 15 is about 40-ish minutes after he takes the soup off. And 10 degrees above room temperature is about 48, maybe 49 minutes after he takes it off. So let's go back and watch the rest of the video.
F of x.
Actually, we're running out of time, so here's the end of the video.